Hello students, today we'll be discussing the topic stereoisomerism of carbohydrate. Let's look at the introduction first. The study of carbohydrates and their chemistry immediately introduces the topic of stereoisomerism. Let's start with the introduction first. The study of carbohydrates and their chemistry immediately introduces the topic of stereoisomerism. Compounds having same structural formula but differ in spatial configuration are known as stereoisomers. While writing the molecular formula of monosaccharides, the spatial arrangements of hydrogen and hydroxyl groups are important, since they contain asymmetric carbon atoms. The reference molecule is glyceraldehyde or glycerose, which has a single asymmetric carbon atom. The subject of isomerism may be divided into structural isomerism and stereoisomerism. Stereoisomers have the same molecular formula and the same structure, but they differ in configuration, that is, in the arrangement of their atoms in space. Structural isomers, in turn, can be of three types. One type is that of the chain isomers, in which the isomers have different arrangements of the carbon atoms. Another type of structural isomers is that of positional isomers, in which the two compounds involved the same carbon chain but differ in position of a substituent group are positional isomers. The third type of structural isomers is that of functional group isomers, in which the compounds have different functional groups. Let's look at the isomers in carbohydrates. First, Fischer projection formula. To show the structures of a resulting molecule, we need to know more about the convention for two-dimensional perspective of a molecular structure, which is called the Fischer projection formula, after the German chemist Emil Fischer, who established the structures of many sugars. Emil Fischer, 1852 to 1919, was a German-born scientist who won the Nobel Prize in Chemistry in the year 1902 for his studies on sugars, purine derivatives, and peptides. We shall use some common 6-carbon sugars for purposes of illustration. In a Fischer projection formula, the most highly oxidized carbon is in the aldehyde group written at the top and is designated carbon 1. In the ketos, the ketone group is at C2, the carbon atom next to the top, or carbon 1. Most common sugars are aldoses rather than ketoses, so our discussion will focus mainly on aldoses. The other carbon atoms are numbered in sequence from the top. The D or L configuration depends on the arrangement of the hydroxyl group or the OH group at the chiral carbon. In the cases of glucose and fructose, this is at C5. Two sugars that differ only in the configuration around one carbon atom are called epimers. D-glucose and D-mannose, which differ only in the stereochemistry at C2, are examples of epimers. Next, let's look at the Howard projection formula. The Howard projections represent the stereochemistry of sugars more realistically than do the Fischer projection, and the Howard scheme is adequate for our purposes. We shall continue to use Howard projections in our discussion of sugars. The structures of alpha and beta-D-glucose, which are both pyranoses, and beta-D-ribose, which is a furanose. In the alpha anomer, the hydroxyl on the anomeric carbon is on the opposite side of the ring from the terminal CH2OH group, that is, pointing down. In the beta anomer, it is on the same side of the ring, which is pointing up. The same convention holds for alpha and beta anomers of furanoses. The alpha and beta anomers of D-glucose interconvert in aqueous solution by a process called mutarotation. Now let's study some terms used in carbohydrate isomerism. Number 1, chirality. The term chirality is perhaps the most important phenomenon related to isomerism. Many objects in the macroscopic world are chiral. All organic compounds which contain an asymmetric carbon atom are chiral. Second, asymmetric carbon atom or chiral carbon. An asymmetric carbon atom is a carbon atom that is attached with 4 different types of atoms or groups of atoms. Lebel-Van Hoff rule states that if n is the number of asymmetric carbon atoms, then the maximum number of isomers is 2 to the power n. Knowing the number of asymmetric carbon atoms, one can calculate the maximum possible number of stereoisomers. Number 3, plane polarized light. A polarized light vibrating in a single plane perpendicular to the direction of its propagation is called plane polarized light. Optical isomers rotate the plane of polarized light either clockwise or anticlockwise. Fourth, enantiomers. The two structures actually stand for positive isomers and negative isomers are related to each other as mirror images. They are commonly called enantiomers or enantiomorphs. Thus, optical isomerism is referred to as enantiomerism. Now let's study the topic stereoisomerism. The subject of isomerism can be divided into optical isomerism and geometrical or cis-trans isomerism. First, optical isomerism. Certain organic compounds, where their solutions are placed in a path of plane polarized light, have the remarkable property of rotating to the left or to the right. If the polarized light has its vibrations in the plane xy before entering such a solution, the direction on leaving it will be changed to x prime, y prime, the plane having been rotated through the angle alpha. This property of a substance of rotating the plane of polarized light is called optical activity, and the substance possessing it is said to be optically active. For the measurement of optical rotations, a term specific rotation is introduced. This is a physical constant characteristic of a substance as much as the melting point, boiling point, density, or its refractive index. It is defined as the degree of rotation observed when light is passed through 1 decimeter or 10 centimeter of the solution having concentration 1 gram per milliliter. Now let's study the chirality or molecular dissymmetry cause of optical isomerism. The necessary condition for a molecule to exhibit optical isomerism is dissymmetry or chirality. Thus, all organic compounds which contain an asymmetric carbon atom are chiral. It is obvious that optical isomers or enantiomers, due to the presence of an asymmetric carbon atom in a compound, differ only in the arrangement or configuration of groups in the molecule. Organic compounds which show optical activity can exist in 3 forms. A. One rotating the plane of polarized light to the left. This form is named levorotatory or direction plus form. B. One rotating the plane of polarized light to the right. This form is named dextrorotatory or direction negative form. An inactive, which does not rotate the plane of polarized light at all. This is a mixture of equal amounts of positive and negative forms. It is a racemic or DL mixture. Organic compounds which have same molecular formula and having some physical and chemical properties but differ in their action on the plane of polarized light. They have different sign of specific rotation. Such forms of the same compound which differ only in their optical properties are called optical isomers, and the phenomenon is termed optical isomerism. Now let's look at the D and L system. The configuration of H and OH groups is changed and the two mirror images are produced. The groups in the second, third, fourth and the fifth carbon atoms are totally reserved so as to produce mirror images. These two forms are also stereoisomers. These sugars are naturally occurring sugars and the body can metabolize only these sugars. Compounds with similar configuration of the asymmetric carbon atom may have opposite sign of rotations, and the compounds with different configuration may have same sign of rotation. In this system, the configuration of an enantiomer is related to a standard glyceraldehyde. The two forms of glyceraldehydes are plus glyceraldehyde or D-glyceraldehyde and minus glyceraldehyde or L-glyceraldehyde. In the name D-glyceraldehyde, the prefix letter D means that the hydroxyl group on the carbon number 2 is projected to the right of the Fischer projection. The prefix letter L in the name L-glyceraldehyde means that the hydroxyl group is projected to the left. The prefixes D and L are used to tell us the absolute configuration. Now let's study the optical isomerism in compounds with more than one asymmetric carbon atom. An organic compound which contains two dissimilar asymmetric carbons can give four possible stereoisomeric forms. Thus, 2-bromo-3-chlorobutane can give four stereoisomeric forms. Such stereoisomers, which are optically active isomers but not mirror images, are called diastereoisomers or diastereomers. Now let's look at the number of optical isomers. In general, the number of stereoisomers for a compound with n distinct asymmetric carbon atoms is 2 to the power n. Since glyceraldehydes contains only one asymmetric carbon atom, the number of optical isomer is 2 to the power 1. An important group of compounds containing a number of asymmetric carbon atoms are the carbohydrates. Next, let's look at geometrical isomerism. Geometrical isomerism is shown by alkenes or their derivatives in which two different atoms or groups are attached to each carbon containing the double bond. Thus, the compounds having the formula ABC double bond CAB occur in two forms and exhibit geometrical isomerism. When the similar groups lie on the same side, it is called cis isomers. When the similar groups are on the opposite side, it is called a trans isomer. Consequently, this type of isomerism is known as cis-trans isomerism. Let's look at the interconversion of geometrical isomers. Geometrical isomers are stable at ordinary temperatures. One can be converted into the other or to an equilibrium mixture of both by heat, by exposure to ultraviolet light, or by catalysts. Let's look at the cis and trans to butene. This interconversion of cis to trans isomer involved the breakage of carbon-carbon double bond. The cleavage of the carbon-carbon double bond requires approximately 40 kilocalorie per mole of energy. Mutarotation was discovered by a French chemist du Franfort in 1846 when he noticed that the specific rotation of aqueous sugar solution changes with time. The gradual change in the specific rotation of a freshly prepared solution of monosaccharide until it remains constant on standing is called mutarotation. Thus, mutarotation is a term given to the change in the specific rotation of plain polarized light when it is passed through a solution of an optically active compound. Literally, mutarotation is a change in specific rotation of a chiral compound due to epimerization. The alpha and beta anomers are diastereomers of each other and usually have different specific rotations. The optical rotation of the solution depends on the optical rotation of each anomer and their ratio in the solution. When D-glucose is crystallized at room temperature and a fresh solution is prepared, its specific rotation of polarized light is plus 112 degrees. But after 12 to 18 hours, it changes to plus 52.5 degrees. If the initial crystallization is taking place at 98 degrees Celsius and then solubilized, the specific rotation is found to be plus 19 degrees, which also changes to plus 52.5 degrees within a few hours. This change in rotation with time is called mutarotation and is explained by the fact that D-glucose has two anomers, alpha and beta anomers. These anomers are produced by the spatial configuration with reference to the first carbon atom in aldose and the second carbon atom in ketose. Hence, these carbon atoms are known as anomeric carbon atoms. Thus, alpha D-glucose has specific rotation of plus 112 degrees and beta D-glucose has plus 19 degrees. Both undergo mutarotation and at equilibrium, 1/3 of the molecules are alpha type and 2/3 are beta type to get the specific rotation of plus 52.5 degrees. In the cyclic forms of sugar, the ring is at the right angle to the plane of the paper. The alpha and beta configuration in the Howard representation depend on the hydroxyl group at the carbon number 1, which is pointing below alpha and above beta. Now we have come to the conclusion of today's lecture. Let's look at some of the points that we have covered so far. Isomers are molecules with the same molecular formula but different chemical structures. Among the different isomers, enantiomers are mirror image stereoisomers. Biochemically, important sugars usually contain 5 or 6 carbon atoms. Their structure includes a carbonyl group in the aldehyde or the ketone group and several hydroxyl groups. In the case of carbohydrate structure, optical isomerism is of paramount importance. Most of the important sugars found in nature have the D configuration. Sugars exist in cyclic forms with 5 or 6 membered rings. Molecules with slight differences in the stereoisomeric character. They have very different biological properties and sometimes give negative adverse effects. In the mutarotation, the specific rotation of aqueous sugar solution changes with time. The gradual change in the specific rotation of a freshly prepared solution of monosaccharides is also very important in stereoisomers. Thank you.